The second example is f of x is given by mod of x by x, and you have to check for continuity at x equals to 0. Now let's see if the limit exists. The first condition is that the limit should exist. The second condition is that the limiting value should be equal to the functional value. These are the two conditions which proves that the function is continuous at a particular point, right? Okay, find the left hand limit. The left hand limit, as you can see, is limit x approaches 0 minus h, right? Since it's the left hand limit. Minus h. So this is equal to minus 1. Right hand limit. Okay. So this is equal to plus 1. Since the limit itself doesn't exist, because the right hand limit is not equal to right hand limit, you can say that the function is not continuous at x equals to 0. Also, you can see that the functional value itself is not defined at x equals to 0. So none of the conditions are satisfied to prove the function is continuous at x equals to 0. So the function is discontinuous at x equals to 0. Okay. Now let's say you have a function like this. The function is defined from a to b, and you have asked to check the continuity at a and at b. Clearly you can see that a and b are the endpoints, because the function is defined from a to b, so a and b are the endpoints at which the function is defined. Now to check at the endpoints, obviously let's say I have to check the continuity at x equals to a. Obviously at x equals to a, there is nothing called left hand limit. So to check for continuity at the endpoint x equals to a, what you need to prove is that the right hand limit is equal to the functional value x f of a. Similarly at x equals to b, to check for continuity of a function, you need to prove that the left hand limit is equal to f of b, because there is nothing like a right hand limit at x equals to b. Okay. Now we have discussed enough regarding continuity of a function at a particular point x equals to a. So at the beginning I had drawn something like this. Continuity can be defined at x at a particular point at a given interval. So we have discussed this part. Now if you broaden this part, we will come to this part, because you know an interval is a collection of particular number of points. So now we will discuss continuity at a given interval. Now when you talk of an interval, you know that an interval can be a open interval or it could be a closed interval, right? Now when you say that an interval is an open interval, that means the interval is defined from a to b excluding a and b. When the interval is an open interval, it is defined from a to b including a and b. Now to check for continuity in a given interval, if the interval is open, you need to check for continuity at all points between a and b. If the interval is closed, you need to check for this, plus you need to check for continuity at endpoints a and b. So this is the only difference. And how to check for continuity at endpoints a and b, that I had already discussed before. Okay, so let's take one example, because you know you are able to solve that example. I hope that you have understood the concept. The question is, f of x is box of x, where this denotes the greatest integer function. Okay. Now you need to discuss the continuity in the interval 1 to 2. Okay, so if you draw the graph of box function between 1 and 2, you see graph will look like this. So equal to 1 when x lies between 1 and 2 is equal to 2 for x equals to 2. So obviously you see that the function is continuous between 1 and 2. The function is continuous at 1, but the function is not continuous as at x equals to 2, because at x equals to 2 the functional value is 2, where the limiting value or the left hand limit is equal to 1. So the function is discontinuous at x equals to 2, or the function is continuous between 1 in this interval. It's discontinuous at x equals to 2.